we're going to open the thing, which is neither a morning session nor an afternoon session, but a secret third thing. And opening up, we're pleased to hear from Yuji Okawa from University of Tokyo Komaba campus, who will be telling us about correlation functions of scalar field theories from homotopy algebras.
And I'm very much honored.
I see microphone is not working.
Can you hear me okay?
Yeah, maybe move up a little.
Is it better now?
Slightly better, but yeah.
Should I use this? I can use this.
Yeah, that's another option. Yes. Maybe microphone is a bit far. 襟につけてはどうでしょうね。ジャケット、シャツの襟。
I like it.
なくても大丈夫ですよ。
Okay.
Yep.
It's much better.
Much better.
This. Honored to speak of this wonderful conference celebrating our recent 60th birthday. Congratulations. Before moving to the introduction, let me start with a review. So by the way, this is the one I really like, but I'm not going to talk about this. And I'm going to talk about my postdoc days at Caltech. So I was a postdoc from September of 2000 to August of 2003. And then, so around that time, Seiberg had written on that non-commutative gauge series, gauge series are based on the non-commutative geometry, can be realized on Brains's extrinsic field. We know how to couple matters to gravity in general relativity, but we don't know how to couple the theory based on the non-commutative geometry to gravity. It is even not clear if it is possible. But once the theory is realized in string theory, we can study the coupling of the coupling to the gravity by calculating this amplitude is one processing and an arbitrary number of open chains. That's what I did with Hiroshi. By the way, the collaboration with Hiroshi was totally different from collaborations I had in Japan. So in Japan, we typically have weekly discussion sessions with a writer or as collaborators. But with Hiroshi, when we come up with a problem to solve, he walks to the nearest blackboard and starts solving the problem at that moment. So there's no time to read papers or textbooks secretly to compensate my ignorance. And during the important stage of the collaboration, so I was mildly confined in his office. The situation is even worse. So in front of the blackboard, to write something meaningful, perhaps 90% of what I said didn't even draw Hiroshi's attention. But then I was desperate and I combined all possible attempts. Then at some point, Hiroshi says, which means I got it in Japanese. And he stands up and then writes a YouTube solution. That's how typically Hiroshi works. Every had a paper. This is the first paper I wrote with Hiroshi. This is a covering the geometry. Then I reviewed this. Then the same technique can be used to calculate the energy momentum tensor of the gauge theory on D bands in the decoupling limit, which is also called the DKX limit or the sensor limit, depending on the context. So we did that second paper. And first of all, we can derive an exact expression for the similarity map by studying the coupling of the non-commutative gauge theory to Ramon gauge field in string theory. See here. This is a second paper, which is certainly related to today. And this is just then. So as Take mentioned, at that time there were joint activities between Caltech and USC. Wednesday, the Caltech people make a trip to USC to participate in the seminar. So in the morning, we took a van to Caltech and going to the USC, then to the seminar. And today, the USC people come to Caltech and participate in this thing. So sometimes we have 2 seminars today, and we have 2 seminars on Wednesday and 2 seminars on Friday. We have 14 seminars only. But it was a very gorgeous selection of seminars, which was in ideal environment for postdoc cycle. One of the such seminars which influenced me a lot was the one by Ashok Sen on open string field theory. Because I was really impressed by the geometric method to describe the string fields using the CST technique. So I think this is papers. And then this is one description of the string state, and this is another one, and this is a description of the subproduct and so on. I was really impressed. So then I got interested in the subject, and I wrote my first paper on string field theory. And I think it is nice, and got the postdoc ticket to MIT. So this is there. So my wife and I enjoyed the transcontinental drive from Catalina to Boston. Actually, we went in the wrong direction. San Diego a little bit, then going north and enjoy Yellowstone, Mount Rushmore, and infinite cornfields, and then arrived at Boston. This is what the end of my postdoc days. So, when I prepared this talk, I realized that my current research is deeply rooted. My postdoc days at Caltech. So the motivation behind the work I'm going to explain today is related to the computation I just mentioned, the management tensor of the Gauss area D-branes in the coupling limit. The aim of this work, I also explain this in a moment, that it is the application to the open string field theory. So this is this photo is more recent. I think it's about 3 years ago. And
You're right.
enjoyed a nice meeting in Florence. Then I took a photo of my 2 pictures, which I admire. So now more into the introduction. So cross-string theory is a consistent theory, including gravity, but it is defined only perturbatively. And cross-string field theory is useful, for example, in the discussion of mass renormalization for atomship, as demonstrated by Ashok and operators. But it will be not promising to use cross-string field theory for non-perturbative definition of string theory. Because this is because gauge invariance of the cross-string field theory is anomalous, and we need correction terms at every root order to recover gauge invariance. So the most promising approach will be to the non-perturbative definition of cross-string theory would be the ADS theory correspondent. What picture is gone in the strict two-energy limit or the Gauss area difference. So it might be useful to consider the theory of difference before taking the lunch. You may think such a theory would be open cross-string field theory. That would be even more difficult to define cross-string field theory itself. But my claim is that it can be described by open string field theory with a source term for gauge invariant operators. This seems to be the case, at least for the bottom string, as a consequence of a few non-trivial facts. First of all, unlike cross-string field theory, gauge invariance of open bottom string field theory is not anomalous, and we don't need correction terms to the classical action. Second, it is in general difficult to construct gauge invariant operators in string field theory. But in class of gauge invariant operators, the constructed in open bosonic string field theory. Actually, those papers also can take. Then I can construct a gauge invariant operator for each on-shell cross-string state. And peculiarly, it is linear interpolation. Maybe the most notable part. This open string field theory is a source term for the gauge invariant operators can be obtained in a special name of open cross-string field theory. And it generates all Farman elements which contain at least one button. This on one button here. So purely cross-string diagrams without any boundaries are not generated But then the contribution vanish in the low energy limit we are interested in, so it is okay. And so it seems to be okay in both cases, but then it is crucially important. It is crucially important whether this can be generalized to the open superset. And the long-standing problem of constructing an action during the Raman sector has been overcome in recent years. But then we still think the formulation of open superset field theory needs to be developed further. But I think we are in a position to discuss how we should use open superset field theory to understand the mechanism which evaluates the agency correspondence. So actually, instead of so usually in discussing constant theory, we can consider that's something I introduced as scattering amplitude. But then in this context, instead of scattering amplitude, we should consider correlation functions of the agent operators. The evaluate correlation functions in the one-over expansion and turn it into genus expansion cross-section theory. Perhaps this step will be the most difficult part, and we need to generalize the watershed derivation of the large geographic topological string by opening the buffer to the superstring. This is also in the Caltech. Yuji was working on this beautiful video. So this is maybe, but then I want to have a framework to discuss this. So the quantum treatment of open string field theory is crucial for this duality, to understand this duality. But the explication will be technically difficult for open superset field. But we need to calculate correlation function explicitly. We don't need to get a number, but we need to understand the structure of the theory in the one. Then homotopy algebra, I think, can be useful too for this purpose. And previously we have used homotopy algebras, such as algebras or every algebras, in the construction of actionable semiconductor theory. However, we might not have fully appreciated the power of homotopy algebras, and then they can be also useful in solving this. So the problem of the rest of the topic is possible. I will explain anything algebra, which is one of the algebra. Then the main result is the formula for the correlation function with scalar. Then I briefly mentioned its application to the renormalization group and analytical. Okay, so open post-time theory is described in terms of string, which is a state of boundary conformal result. The Hegel space of this theory can be composed based on the Gauss number. And the critical action is written in terms of the string field in Gauss number 1 sector. Then we consider action of this one. So this is kinetic term. This is cubic interaction. This is called interaction. So if we use in a product, also then the answering product, This action is invariant up to for the G cube and the gauge transformation with this kind of parameter in the most number zero sector.
Excuse me. So are you considering like more some certain general framework of open string field theory, not necessarily like that of Witten's cubic?
Witten theory is also in this way.
So we can also understand Witten's open string field theory in this context.
In that case, we don't need this field.
Okay.
But then we can homogeneize.
I see.
It is open superset field theory. It's every dimension. This action is invariant. The gauge transformation generated by the same using the same set of the numbers in the this one, and the should be invariant under this case transformation if matches are important satisfy these relations. This relation we need for up to for the GQ. So this relation can be extended to higher orders, and they are called infinite relations. In this domain, I'm not talk about the and so on. But this is rather complicated. So let me try to simplify the description of infinite relations in 3 steps. Step 1 is to introduce degree. So we usually graded this is respect to the Grassmann parity. Somehow we introduce degree, which is shifted by 1 or 2 from Grassmann parity. Then 6 by the 1. Then instead of the VPs in the product, we use omega, which is now graded Anderson. And then these are the multiples of numbers. So is to introduce so we consider the tensor product of n copies of period space and denoted by h to the n. Then we consider the map from h to the n to h denoted by this. And technically, we also need zero strings and the space for the zero string space, which is denoted by h to 0. It is just one-dimensional vector space, and this is vector about this.
So have you defined Cn? You define Bn and Mn?
This is multi-string product. This is rather simple. So we consider
What's the relation of Cn to B or M? Are these not related?
These are okay. Bn is the one of the examples. I just use a modular knowledge. Multi-string product. So you can just think of this as Mn. And then I use the same symbol, but this can be understood as a map from h to the n to h. So this is argument. So it's you may not appreciate why this is useful, but
Okay.
actually, once we write this, then previously we need A1, A2, A3, and so on. But now we can rewrite the infinite relation as an
Okay. Yeah, I see.
That's into
I see.
And as you see, small and all the signs are not wrong, so it's very simple. And notice relation from H to H. There's many items of that slightly change them. Yeah. Then step 3 is the so we use co-derivations. So it is convenient to consider linear operators acting on the vector space PH, which is the sum of all those sectors. H0, HS, H2, H squared, H2. So this is a arena we consider. And then we denote the projection operator onto Hn by Im. So you don't need to follow the notation, but the Im appears frequently, so please remember only this notation. Then from a map Cn, which is an from H to the n to H, we define the associated operator, a bold-face Cn, which may not be but then for Mn it is actually bold-face.
So this is not the same as Cn in the previous slide.
Slightly defined, but maybe I don't. But maybe. Can you see? This must be more visible. Anyway, so in the next slide, so this is visible. So this is 1%. So the Cn is not. So this is the previous Cn, and this is the bold face. So anyway, so from Cn we can define operator acting on this TTH. This kind of generation. So I will not explain in detail. Then, so but if you remember this structure, which you already seen in the previous simplification, so this relation can now be written compactly as just an m squared to 0 by introducing this of the time on TH.
Mhm.
And this operator of this one is called coordination.
This is not related to BRC operator, or this is related?
This is not related to BRC. Typically, so first of all, BRC operator can be understood as one string. Then we have a boldface Q. So if you do not ordinary.
No, but for example, it is true that a V1, which is like a original Q acting on the first quantized Hilbert space,
Yeah.
is nilpotent.
That's
But for example, in the Witten's cubic string theory, for example, you can also consider Q plus A.
That's right.
And then square of Q plus A is 0. And that's, but isn't this like a generalization of this?
Yes, this is it is exactly the same. So in the case of Witten theory, this M is just a Q plus M for describing the Q.
Yeah, but in Witten's case, that equation is the equation of motion for A. So it's not, but here it's an identity, right?
This is it is
Because in which case that's the condition for A.
this is the condition for gauging.
Right. Yeah, that's right. Okay, okay.
Yeah, this is gauging. So this is the Q strategy.
Oh, I see.
This is the inversion property of Witten's.
I see.
But I'm explaining it in more general.
I see. So it's more like I see.
Yeah.
Okay.
So if we have the degree of co-derivation on TH, we can have a gauge invariant action.
I see.
That's it. The pitch scale to 0, and now we have gauge invariant.
I see. I understand. I understand. Thank you.
So, compared to this messy equations, we have succeeded in simplifying the equation relation. Then, if you consider projection on the subspace of H, homotopy algebra, it can naturally provide a useful tool. So if we consider projection onto on-shear state, then we can describe on-shear scattering. This is based on the work of the algebra. And if we consider projection onto on-shear state, or projection onto physical sector, then this can be used to mapping between the covariant and the right constant cases. And the most relevant one is this projection to the mass. For example, in the projection to the mass sector, useful is relevant for the long-range interaction, which is originally discussed by Michel in close to time context. But this can be understood in the framework of homotopy. So in this case, we decompose M by free part and interaction. Q is described the free theory. We can just include the BRC operator and it's co-derivation sensitive to the BRC operator. That's why I did not do Q. And then it is for interaction. And then we consider Q, which we consider projection, which we just said. We denote the projection operator by P, and this can be, we also promote this P to the boldface P on TH, then the relation can be extended to the boldface operators. The one more important ingredient is a propagator. So in the context of the projection of the massless sector, the propagator for the massless field is biased. And we denote the propagator by H, and we again promote this H to the boldface H on TH. This is certainly here. Then we have all those relations operators on TH. Then this is an important point. So the important point, the theory after the projection inherits the infinity structure from the theory before the projection. So if the theory before the projection is described by Q plus M, this is a degree of coordination, it's scaled to 0. Then the theory after the projection is described by this form. This is known as homological perturbation. Also, scattering amplitudes at a 3 level can be calculated from this formula if you use the projection to the massive projection to the on-shear state. And furthermore, on-shear scattering amplitudes at a loop level can also be calculated by extending infinity algebra to quantum infinity algebra, which I'm not to be explained later. But stronger for the quantum infinity algebra, has not been explored. And in addition to the scattering amplitude, we are also interested in correlation function. So actually, many actions are written in terms of the homotopy algebras. The expression on shape scattering amplitudes are universal for string field series and ordinary field. So let's study scalar field theory in terms of quantum and algebras to gain insight into the quantum aspects of string fields. So that's the motivation. And also, we find correlation function can be described in terms of homotopy algebra. And I'm going to explain this formula.
What is meant by universal? The same formula applies?
Yeah. So basically, this one.
Okay.
You can describe scalar field series in this language. Regarding the scalar field series in this language itself is not very important. I don't think it's useful. But the relation between the action and the scattering amplitude are universal. That's fine. So you may explain the formula for correlation functions for scalar field series. So let's consider phi Q theory in beta dimensions. So this is the action. And to describe this action in terms of algebra, actually in this case we need two copies of the vector space of function domain. So in general we need sectors for the scalar. In the scalar field, we need two sectors. So, H1 and H2. That goes number 1 goes number 2. And we define omega Q and M. This is a software and this. Then in the structure of the group selection is the extension of these operators, the board face operators. But if the relations are trivially satisfied the theory without occasional. So as I just said, so derivative induction in this one is not very, this is just a trivial function. You maybe consider on-shape scattering amplitude, and also we need to define H. So this is just a standard property. In the case of the projection of the on-shape space, so this is a universal formula. For this case, exactly in that function. So this one is equivalent on-shape scattering. Then when we discuss the quantum theory, we also need to include the counter terms, and the counter terms is included in the injection part of this. This is it is included this part. The amplitudes, including loop diagrams, can be calculated by generalizing this formula to this. So we need to have this matrix. So I mean this and we can so the amplitude that was claimed. This operator U consists of a maps from H to the N to H to the N plus 2. So basically, this is incorporates here the basis space of H1, H2. So when the vector space H is given by H1 and H2, the operator U incorporates a pair of basis vectors of H1 and H2. So we note the basis vector of H1 by the label basis vectors, and then for H2 we use our output. And also we can use this kind of basis for the calculations. So action of this operator U on H to 0, just to pair of basis space, and action of H on U on H, you have basically and as the alpha we have in both ways. So now every algebras are extended to quantum theory. Again, I will not explain the effective engineering for the quantum effective algebra, then they are trivial and satisfied for the theory without gauging that. So this is what is discussed previously. So but if you recall that the projection operator, projection onto the massless texture correspond to the integrating out the mass integral. So carrying out the mass integral completely should correspond to the projection to nothing. Then in the case, we promoted this operator to order P on this way. So this P, so for this injection, the order P is just an integration onto the delta. So this may sound trivial. So this may actually result in trivial theory at the classical case, but it can be non-trivial for quantum case. And in fact, this is exactly what we do when we calculate correlation functions. So my claim is that the function, so I just changed the Euclidean space, which is I think it's more Euclidean setups. That's not the scalar field series. Euclidean space, we define the important f by this which corresponds to previously this seems to be the important part, so which I didn't here. And then this is the one of the approximate. So this in this case corresponds to this expression for the Euclidean. So say so if you calculate PMF this vanishes, but f itself is not vanishing. And my claim is that this operator plays a central role in generating Feynman diagrams, and if we claim that information of correlation functions is encoded in this associated with the projection to nothing. More explicitly, the correlation functions are given. So basically, this may be complicated, but basically the endpoint function is encoded for the operator INF. So this is part of F from up to h to 0 to h to n. And then you don't need to follow the formula. Actually, this is rather simple. So once, for example, in the case of if you're interested in a 3-point function, this is the relevant sector, F1. And if it is written this way, the correlation function is simply replacing x in the first sector to x1, x to the second sector to x2, the third to x2. This is just a simple replacement group. So if you know this I3F1, then you get information of the 3-point function. If you know I and F1, then you get the correlation function for endpoint functions. So I will not explain the details of the correlation function in this book, but let's see. Just demonstrate that for the free theory, a 2-point function is given by this, and it has x to x1 into x to x2, and you get these properties. And for 4-point function, basically, we need to calculate this I4 F1. So this contains 3 terms, and each corresponds to the product of the propagators. So this is external, and it is not difficult to generate and extend it to 6-point functions and higher. Then this is for the free theory. So we are interested in quantum theory, especially 5-cube theory, and then also previously there's no work on the renormalization and so on, so that's I want to make sure if this can be because all the fabrication the textbook of quantum theory can be used. So the 5-cube theory, so this is the action including counterterms, and we expand counterterms in G as usual. Then the function is given by this. So this reproduces the sample diagrams. In particular, the symmetry factor, which is actually the symmetry is correctly reproduced. And For example, the two-point function can be we calculate this, and it contains a discrete part and commutative part, and commutative part is in values, and again this the sample result. I'm pretty sure all the part of the calculation of the asymptotic or canonical conservation can be reproduced in this range based on the conservation. And furthermore, we can show, I will not explain this in this talk, but we can show correlation functions formula satisfy the Schrodinger's equation. And actually, it is a direct immediate consequence of this relation. So this is the F, this is just it is the inverse of this. If you integrate this, this can be easily understood than Schrodinger's equation. And we can also extend this formula for correlation function to incorporate the experiments. That is progress is a student of mine. Case so this is the formula for correlation functions. Then I'm gonna explain its application to the normalization. So especially the construction of the bold-face operator H from H is not unique. So in addition to the projection to 0, we can introduce a projection for projection of the modes below certain energy scale now. So we can do the percentage in 2 steps. So integrate out the higher energy mode. Then in the case we can construct the board face H, which satisfies the same algebraic relation, this way, H and HL. Where HH is a propagator for high energy modes, and HL is for low energy. Then this is the operator which contains information on the correlation functions, and it is just a simple algebra of linear. This is a simple calculation of the linear algebra. We can write this operator in this product form, and this part involves only the high energy mode, HH and original. And this is for the low energy. And then this n lambda can be understood as a Wilsonian interaction at the energy scale lambda. That is, so a correlation function can be expressed in terms of product of two factors, which involve only high energy modes and low energy. We can further consider the sequence of the solution. So that corresponds to the integrator of the sun energy scale and scale and so on. Then we can write the correlation, the operator which contains the information of the correlation functions in this product form. This is very nice because, for example, if you expand this, typically you get the Feynman diagram, something like this. But then, so for this region, we use so this corresponds to the integration of the high energy modes. Then we use the vertex at the energy scale, UV action, and then this product is corresponds to the integration over the middle energy scale, and then for this interaction is the Wilsonian interaction of the energy scale, and this is so this so previously the perturbative expansion of the correlation function is previous H or face H. It's reproduced all the perturbation theory, but I don't think it's converged. But then if you consider this sequence of projections, this choice of H can be undefined number theoretically. So this may lead to the non-perturbative expression of the correlation. So let me summarize. So we propose the formula for correlation function with scalar fields interpretation theory using this compound and algebras. So as I explained in the introduction, so our ultimate goal is provide a framework to prove the ADCT correspondence using the open string field theory. Is a gauge invariant operator, source gauge invariant. The quantum treatment of open superstring field theory is crucial for this program, and I hope this quantum and algebra will provide a useful tools in this area. So I think I have convinced you that this talk is deeply related with my postdoc days at Caltech, and I will take this opportunity to thank all the time for doing such a wonderful experience. Thank you.
Questions for, yes.
Yeah, so toward the end, you discussed this algebra in the context of scalar field theory, but this applies to open string field theory, initially motivated by open string field theory.
Yeah, that's actually as far as universal, but that's almost so. So technically, it's small application.
So which part is strictly applicable to open string field theory, and which part is applicable only for scalar field theory?
So some of the detailed communication simple, because of the condition that we have only two sectors.
Okay.
That part is not applicable. But for example, when I try to prove that the this explanation, I will not able to prove in general cases.
Oh, so this identity, although this looks rather general, but it's only applicable to scalar field.
Yeah, but I think there's a way. So we haven't been able to prove it in general case, but I think it should be the case. But then technically,
oh, I see. So so that was sort of related to my second question, which was that this looks like rather universal way of writing renormalization group equation. So I was wondering whether there is a connection to Korchinski's renormalization group equations.
So this, I think if you because this is a sequence solution, but then you can deal with the differential equation,
right?
For the how you change the energy scale number to the number plus delta number.
Yeah,
I think you can describe the Korchinski.
So this is actually integrated version of Korchinski's equation.
So more algebraic way, well, expressing the exact generation group for this other. So I think it is going to be useful. So that's
great. And so my third question is that so most of what you said are applicable to open string, maybe some part there is technical simplification. How about cross string fields?
Cross string fields. So first of all, cross string infinity algebra is more is naturally the open string field theory is naturally expressed in terms of infinity algebras, and cross string field theory is naturally expressed in terms of infinity algebra.
Okay.
And but most of the discussion can be so. Then my motivation is to use the open string field. That's why I use infinity language. But then most of the calculation can be extended to infinity algebra without much change. I think that's so. There are nice formula for this kind of. It's what actually it's a simplified simplified version of this vector. And then we can consider this kind of coordination for any and actually most of the calculation can be extended to n. So that's I think we can extend to the close.
Can you also write the analog of renormalization group equation in that case?
Yeah, I hope so. Yeah.
Because I asked this because cross string, of course, contains gravity.
Yes.
So there might be some subtlety with renormalization equation. So
I just have a scalar series. Next step is just with a gauge, ordinary gauge fields. In this case, we need four sectors: H0, H1, H2, H3. Then and if we can, from 2, 4%, that's okay. So that's my hope.
I see. Yeah, so talking about use of this infinite algebra, so there's a text, there is a book by Kevin Costello, where he sort of tried to understand perturbation and renormalization of quantum field theory in a more mathematical, rigorous language. And the infinite algebra and battery Minkowski equations is one of the tools he used. So are there connections to what you did and what he was doing in the book?
Yes, they're closely related, but I don't see. So, for example, so controversion, homotopy is one. I look at the literature that no, I think there are many things to issue.
Yeah, but for example, I think main point of Kevin's book was to actually build up this quantum aspect.
Yeah, some analog of the projector is yeah in his book, I think, but maybe not the quantum infinity aspect.
I see. Thank you. Thanks. Too many questions. I should go.
Thank you.
Sorry, yeah. Want to ask technical questions? Can you include composite operators in the correlation functions? Yes.
Yeah, actually, so when I prove the I just basically you can consider composite operator. Just choose. So yeah, just define composite operator by taking development the same. But you need to so you first regularize like I'm splitting and add counter term and take the then you can define composite. Just like that. I'm on that. We do the confused.